Hi everyone, it's Mrs. Meehan, and in this screencast, I'm going to connect net force and Newton's second law of motion. So when we're talking about a net force, that relates to the formula that is Newton's second law of motion. So that sigma F equals ma. So sigma F, that sigma there, that weird looking E, it's a Greek letter sigma, which means the sum of. Sometimes it is written as F net or net force, but those mean the same thing. So sigma F and F net both mean that you should add up all the forces acting on an object. So that means that that is going to be a sum. Now you'll also notice sometimes there is an arrow above the F here, and this reminds you that force is actually a vector quantity. So we won't always write the arrow, but just remember that it's there. So what this means is that when you add forces, you have to add them like vectors. Forces have direction and they can cancel out. Let's try an example. So the problem here is we have a 5 kilogram object and it is being acted on by a 20 Newton force to the right. That will be F1 or force 1 in this problem. And there is also a 30 Newton force also to the right. That will be F2, force number 2. So the question is, what is the net force on the object? So our first step with this type of problem, even though it might seem a little straightforward right away here, it'll be good practice for something called a free body diagram. So we will discuss these in more detail later on, but for now, just follow these simple directions. Free body diagrams, or FBDs, consist of a dot representing the object and arrows representing the forces. The direction of the arrows represents the direction of the forces, and their length is roughly proportional to their size. It doesn't have to be perfect, but you do want to somewhat draw them to represent the size of the forces relatively. So in this case, for this problem, we have force number 1 right here. And so this first force acts to the right with a magnitude of 20 newtons. So you'll notice we have the dot here. That is the object. And we have force number 1 acting to the right. So you start at the object there and draw an arrow to the right, and it'll roughly represent about 20 newtons. Now remember, we do have an additional force present. So that will be the 30 Newton force to the right, force number 2. And it's in a different color, just to show the difference there. But they're both acting in the same direction. Remember, they are vectors. And this one is drawn a little bit longer to show that it's a slightly larger force than force number 1. So we have force number 1 here, which is the 20 Newton force, and force number 2 here, which is the 30 Newton force. Now this is an example of something, or it's an example of vector addition. So we have the arrows here representing vectors. So they have a direction and they also have a relative magnitude here in the picture. And we know what the exact magnitude is from the word problem. So to add them up, you'll move the second vector so it starts where the first one ends. So the sum is a vector which starts where the first vector started and ends where the last one ends. So it's starting to look like this. We've got 30 newtons essentially, or 20 newtons plus 30 newtons here. Force 1 plus force 2. So these free body diagrams, as we'll see later in the unit, are critically important to our work. Once they are done, the problem can be translated into an algebra problem. So the first step here is we're always going to define to the right as a positive value. Then we can interpret our diagram to read net force equals force 1 plus F2. filling in the values, we have 20 newtons plus 30 newtons. We can also see that in the diagram, which adds up to 50 newtons to the right. So we get the direction from our diagram and from our positive answer, which we defined as meaning to the right. So with the diagram, we know that this positive value is to the right and not up, for example. Okay, let's try a couple practice problems. So we have two forces acting on an object. One force is 40 newtons to the west, and the other force is 40 newtons to the east. What is the net force acting on the object? So what we are given is force number 1, which is 40 newtons to the east. Force number 2, we'll say it is negative 40 newtons to the west, since now that is in the westward direction. Remember, with vectors, we want to note algebraically using the positive or the negative sign. If we looked at it as a diagram, we have our 40 newtons to the east, and we have our 40 newtons to the west. Anything to the left of the object would be the negative direction, and anything to the right would be the positive direction. What is the net force in this example? Well, net force is going to be the sum of all forces. So force 1 plus force 2, that equals 40 newtons plus negative 40 newtons, which is the same thing as subtraction here. So we end up with a 0 Newton net force. Two forces act on an object. One force is 8 newtons to the north, and the other force is 6 newtons to the south. What is the net force acting on the object? Okay, so we're given two force vectors, but they're in a different direction from the last problem. In this case, we're talking about north and south. So north would be considered positive direction. So here's our object. Anything upwards or above the object would be considered the positive value, and anything below, downwards, would be considered the negative value. So again, we're seeing the forces cancel out because they are in two opposite directions. And since they're vectors, algebraically, we represent that using the positive and negative symbols. So again, you see we have the 8 newtons here, plus the negative 6 newtons. So that removes some of the force since it is in the opposite direction. So what you end up with as the net force is 2 newtons, and to the north, since we still have a positive value. If this ended up being a negative value, then that would tell us that the direction was to the south. Okay, so let's take a look at the right side of the equation now, the ma, mass times acceleration. Mass is a scalar. It does not have a direction. You can't give that quantity a direction. It's just not possible. But acceleration does have a direction. So thinking back to the kinematics unit, acceleration is a vector. The direction of the acceleration vector is always the same as the direction of the net force, sigma f vector. So you want to keep that in mind as you solve these problems. If acceleration is to the right, then that means the net force must also be to the right. The same thing if acceleration is to the left, the net force will be to the left, and the same rules for up, down, north, south, etc. So let's go back to the problem here. We have the 5 kilogram object being acted on by a 20 Newton force to the right and the 30 Newton force to the right, both of them to the right. We found the net force on the object to be 50 newtons to the right. So this object is moving to the right. Since the object is moving to the right, we know that the acceleration must also be to the right. So let's take a look at this more closely. So we have our equation, sigma f, or net force, equals ma, which is mass times acceleration. We want to find the acceleration, so let's rearrange this. We'll divide mass from both sides so that we end up isolating acceleration. which will be equal to the net force over mass. Now we know the net force from the previous step. We calculated that to be 50 newtons to the right. It is a positive value. So we have our 50 newtons. And we also have the mass, which is the 5 kilograms. When you do that division, you end up with an acceleration of 10 meters per second squared, which is those are the units for acceleration, remember. And notice that this is also a positive value. So that indicates that the direction is also to the right, or the acceleration is in the same direction as the net force. If you ended up with a negative net force, that would give you a negative acceleration. All right, let's take a look at a slightly different example. So what is the net force acting on the object below? Recall, force is a vector, so sigma F equals ma is true along each coordinate axis. So we're looking at something here in 2 dimensions now instead of just 1 dimension. We're looking at the horizontal axis, that dimension, and also the vertical axis. The information that we're provided is that there is a force. Force number 1 is acting upwards. Force number 2 is acting downwards. Force number 3 is acting to the right. And we have an acceleration of 1 meter per second squared, which is also acting to the right. So let's take a look at it from each direction. So for the vertical direction here, we can add up the forces. Now a hint from here is that since the object is accelerating to the right, that means it matches the force acting to the right. So the force acting to the right is causing acceleration to the right, meaning that these first 2 forces here, the vertical forces, are not impacting acceleration at all. That would mean that the vertical acceleration in this case is 0. So looking at this step here, we have our force 1 plus negative force 2. Remember, the negative symbol is what makes this a vector. Force number 2 is acting downwards, so it is a negative value, equals ma. So this force 1 minus force 2, that is the net force, the left side of the equation. So that is just showing it broken down, that you're adding up all the forces involved in this direction, equals ma. And acceleration is 0 because this object is not moving in either of those directions. So that means that the net force must equal 0. There's no acceleration happening in those directions. So since that equals 0, then the net force as a result equals 0. There are forces acting on it, but they're not causing an acceleration, so those net forces will be 0. Now in the horizontal direction, we know that an acceleration is being caused by this force. So this net force is going to be greater, it's going to be a non-zero value. So we have our force number 3 here equals ma. Let's say this is an object with a mass of 2 kilograms. That means we have a mass and we have the acceleration given. So 2 kilograms times the 1 meters per second squared means that force number 3 here is equal to 2 newtons. Okay, let's try a few more practice problems. A force F1 which equals 50 newtons, acts to the right on a 5 kilogram object. Another force on the object, F2 equals 30 newtons, acts to the left. Find the acceleration of the object. Okay, so the net force here will be the sum of all forces. So we have force 1 and force 2 in this case. Force number 1 is 50 newtons, and force number 2 is negative 30 newtons because it is acting to the left. So remember, if something is acting to the left, it will be assigned a negative value algebraically. So it is essentially 50 newtons minus 30 newtons, which equals 20 newtons. Next, we want to find the acceleration. So net force equals ma. If we rearrange it by dividing by mass on both sides, we get acceleration equals net force divided by mass. Plug in the values, so we have acceleration equals 20 newtons, that's what we determined to be the net force above, divided by 5 kilograms provided by the word problem, and you end up with an acceleration of 4 meters per second squared. A force F1 equals 350 newtons pushes upward on a 20 kilogram object. Another force F2, which equals 450 newtons, pulls downward on the object. Find the acceleration of the object. So let's list out what we are given. We are given force number 1, which equals 350 newtons up. Force number 2, which equals negative 450 newtons because it is down. Remember, anything down will be assigned the negative symbol. The mass is 20 kilograms, and we're trying to figure out acceleration. So let's look at the left side of the equation first. That's net force equals the sum. So in this case, there's two forces acting here. We have F1 plus F2. F1 is 350 newtons minus the 450 newtons of force 2 will equal negative 100 newtons. So remember, force is a vector, so we can end up with a negative symbol in this case. Now let's take our second law equation, rearrange it to solve for acceleration. So acceleration will equal net force divided by mass. Plug in the negative 100 newtons from above for net force. Divide it by the 20 kilograms of mass provided from the word problem. And you end up with negative 5 meters per second squared. So since there is a negative symbol and our forces were acting up versus down, we know that the acceleration will be downward. So it will match the downward force, the downward net force that we solved for above. An object accelerates downward at a rate of 4.9 meters per second squared. If the downward force on the object is 500 newtons and the upward force is 250 newtons, what is the mass of the object? Okay, so let's see what we're given here. Breaking down the word problem, we're provided an acceleration. In this case, it is downward. So since it is downward, this would be considered a negative acceleration. So negative 4.9 meters per second squared. Force number 1 is directed upwards, so 250 newtons up. Force 2 is 500 newtons down. You could also rewrite that as negative 500 newtons, since it is downward. And we need to solve for the mass. So first, let's solve for the left side of the equation. Net force will be the sum of all forces. So we end up with 250 newtons plus negative 500 newtons, which equals negative 250 newtons. Then we need to solve for mass. So instead of dividing dividing mass from both sides, we'll divide acceleration from both sides. So mass will be equal to net force over acceleration. Plugging in the value from above, we have our negative 250 Newton net force divided by the negative 4.9 meters per second squared acceleration, which was given. You end up with 51.02 kilograms. And notice that this is a positive value, it is a mass, it is a scalar quantity. So you will never end up with a negative for mass. Okay, your final step is to work on the correlating practice problems. Those would align with the chapter problems document, numbers 5 through 9 and 15 through 19. As always, let me know if you have any questions or need extra help.